Aerodynamic efficiency. What is aerodynamic efficiency? Well, it is the degree to which a body cuts through a fluid with least resistance. In other words, how easy it is for an object to move through a fluid. But why tackle this problem? There are many reasons why this could benefit us, but I'll give you 3. Fuel efficiency, environmental impact, resource conservation, and application with other modes of transport.
Fuel efficiency and environment. Having better aerodynamics means having lesser drag, which means the required amount of fuel will be less, leading to less greenhouse gases and benefiting the environmental impact.
Number 2. Resource conservation. Think about it. Better aerodynamic efficiency means you will need a lower required power to maintain or push the speed of a vehicle. This means you won't have to spend extra expenses, labor, and resources to develop a stronger powerhouse if the solution is literally outside the box.
Last but not least, we have transportation. Did you know that motorsports such as Formula 1 actually helps innovate transportation developments? Things like pedal shift gearboxes, hybrid engine systems, and active aerodynamics.
When activated, this top rear wing flap instantly rises. The flap closes automatically when the driver hits the brakes.
By understanding how certain factors can come into play, engineers can use this information to improve and innovate modern vehicles other than cars as well.
Now moving on to the theory. Well, if you're here for the experiment, you can skip to this time frame. But if you want to stick around for the theoretical explanation, then you can stick around. Now, what's the first thing that comes to mind when traveling at incredible speeds? We think of stuff like the Concorde or the SR-71, and what do they all have in common? A pointy, sharp nose. So does a pointy nose equivalent to faster, more efficient travels? Turns out it depends. You see, there are differences between subsonic and supersonic airflow behaviors. When it comes to supersonic flow, the characteristics of airflow changes, with the airflow being compressible and temperature and pressure spiking instantly in shockwave formations, and its biggest drag factor being wave drag. But today we'll be dealing with normal subsonic speed vehicles. In subsonic speeds, things are a little different. Airflow is actually incompressible and with temperature and pressure changing gradually along the body, with its main factor of drag being pressure drag and friction drag, which is under one category, parasitic drag.
Now let's talk about pressure drag. Pressure drag is the retarding force caused by the difference in air pressure between a higher and lower region of pressure, pushing the moving object against the forward movement with turbulent weight pulling behind it.
Next, let's move our focus now to skin friction drag. Friction drag is a retarding force caused by the shear stress and molecules from air resistance sticking onto the outer surface of the moving object as it moves through the fluid. Because air isn't completely smooth, alright? Air molecules stick directly to the skin of a moving object, like a microscopic friction rubbing against it and dragging it back as it moves.
Now remember the question if a pointy nose makes things faster in subsonic speed conditions? Well, take a look at this. We have 2 designs. First is a streamlined shape, rounded nose, tapered end. In the second design, we have a sharp pointy nose and a flat end. Okay, so let's take a look at the streamlined body. At the nose stagnation point, oncoming air stops completely to form a high pressure region zone, while the gentle curves keep the split airflow smoothly attached to minimize form drag. However, because of this elongated streamlined shape, it increases the surface area exposed to air, hence friction drag being more predominant and being the main resistance force. Okay, now for triangular body. At the stagnation point, incoming air stops and creates a high pressure region zone same as before, while the nose harsh angles forces the airflow to squeeze violently up the slope. So this rapidly increases the acceleration and it creates a severe low pressure drop via the continuity equation, where they state that a smaller error will increase the velocity of the airflow. And as well as the Bernoulli's principle, where the faster the velocity, the lower the pressure. This extreme pressure difference between the nose and the slope generates far more form drag than the streamlined body. To make matters worse, the sharp corner forces early flow separation, leaving a turbulent low pressure vacuum wake behind the object that pulls it backwards and makes pressure drag the more predominant force. However, overall the streamlined body is the faster pick. Now, this is because after some research, 90% of parasitic drag is actually pressure drag, which means minimizing that 90% as much as possible means minimizing the overall parasitic drag. Alright, so now enough with the theory. Let's get into the experiment to see if the theory even stands.
We have two designs, design 1 and design 2. Our hypothesis, with all the research we can find, is design 2, the streamlined design, will have better aerodynamic efficiency. This is how we're going to conduct it. We're going to set up a ramp to release the modified cars, which then enters a tunnel. At the end of the tunnel is a fan, blowing into it as air resistance. We record 3 attempts per design and average the distance, and based on which design travels furthest is deemed the most aerodynamic.
Hello everyone. So, my group has decided to do question 3 for Fluidmech project, and I've been tasked to make the ramp slash like rail that the car will ride on. So since we're using Hot Wheels car as like the base, I'll be following the overall geometry for like the orange rail that Hot Wheels usually go on, which is basically the track channel at 24mm, and I'll be making it out of that piece of cardboard there. I'll probably make like a time lapse of it. Okay, so like the reason I'm remaking the ramp, right, is because this is alright. What the fuck? And also I just need better cardboard. This too flimsy. And surprisingly the like the ramp, like this ramp part, it needs to be taller. I made it too short. And also I'm gonna go buy hot glue tomorrow, and actually no, I'm just gonna buy hot glue. And it's like, you know, like what the f. You know, the tape's like barely sticky, and it's the only tape I have. So yeah, crazy I guess.
So Ryan went ahead and built the construction like I assigned him to, with the given instructions and dimensions and everything like that.
Okay, so this is basically all the materials for the ramp in terms of cardboard wise. Okay, so as you can see here, I made the ramp like 3 cm because it's supposed to be like 24, right? But I'll give a little bit of like tolerance.
And everything was handy dandy, is what I would have said if it is, but it isn't. We made the ramp too narrow. And it didn't work. But no biggie, I just had to step in and modify the ramp, and here is the experiment. Design number 1. 32 centimeters. Attempt number 2. 3 centimeters. Attempt 3. 31.5 centimeters. Here is design number 2. 40 centimeters. Attempt number 2. 39 centimeters. Last attempt. 44 centimeters. Okay, so I'm in the middle of editing here, and I realized I forgot to record the part where I showed the table for the results. So I'm just gonna show it to you here right here. Here it is, the table of the results. Oops, here it is. So you can clearly see that design 1 travels a shorter distance compared to design 2. So our hypothesis of design 2 being faster is correct, which means our theory lines up with reality, which is wonderful news, and we did not mess this up at all.
So clearly, our hypothesis is correct. And honestly, I'm glad that it is correct, because either I got a theory gravely wrong or I did something wrong with the experiment. Anyways, this concludes today's discussion. We have talked about the two elements to parasite drag, how the continuity law and Bernoulli's law come to play, showing off its real-life demonstrations, and also explain why it's important to understand such things in terms of innovations in transport or otherwise. That will be all for now, and thank you for your attention.